Dr. Russell, are you working on this worksheet today that you have up?
Yeah, it's let me see if I can put it in the chat. Uh, let me pause recording right quick. All right. Um, all right. So we're gonna start today. Let me put some on here. What's the day? 15th. Man, this month is flying by. We're halfway through March already. Um, Dealing with substitution and elimination. And I didn't want to send the videos yesterday because I know y'all had the exam and all that. I still got to figure out how to put file submissions on that exam, but I'll have it figured out by the time we take the next test. All right. So we're talking about substitution and elimination, and we're going to talk about if you took the class with me in part one, we went over this already, but we just didn't go into great detail. But we're going to talk about two types of substitution reactions, SN2 and SN1. And then we're also going to talk about two types of elimination reactions, E2 and E1. Right now I have them written like this because the SN2 and E2 and SN1 and E1 have similar characteristics. Um, and so for SN2, it's a second order reaction, which means that the rate law is going to be dependent on the and for the SN2 rate is, let me not use an equal sign. It's the rate constant times the substrate concentration and then the nucleophile concentration. And then for E2, it's very similar. Just instead of the substrate, it's a base. I'm sorry, instead of a nucleophile, it's a base. So the base times substrate, and then for SN2, it's the nucleophile times the substrate. All right, so that's what we mean by second order. And then for uh, SN1 E1 is first order, right? So it's different. So the rate law looks like this, and this matters when you talk about uh, when you think about the energy diagram, when you think about uh, the concentration. What if you change one of the concentrations? That's what matters. That's why this matters. So the rate is for SN1. K times the substrate. And it's the same for E1. Some of this is redundant because we talked about it in part one. Right. And then as far as like the products are concerned, there's some things that you can do to determine uh, which reaction happened. There's also some other information that we can look at to figure out whether something is SN2 or SN1. So we're going to run through the first part of this handout like pretty fast because um, that some of this is redundant. I think I used the same handout, or at least the first part of it, in part one when I taught the class for part one. I want to change this first example just to give just to make a point, because we talked about this before, but I want to reinforce it. Right, so this is my substrate, and this is an SN2, right? This information up top is everything you need to, well, not everything, but some of the important characteristics of an SN2, right? You can't do it on a tertiary carbon. It's always going to be a primary or secondary carbon. And then it must be done in an aprotic solvent. We're going to talk about why it has to be done in an matter of fact, let me add a page so I can bring that out. Why it's done in an aprotic solvent. We'll talk about that. And somebody tell me what the definition of aprotic is.
Doesn't it mean it can't donate H plus?
Right. It's not acidic. It cannot give up H plus. Um, and so let's do the problems first, and I'm gonna talk about why the aprotic solvent is important for this reaction. All right. So what would the product be for the first reaction? It's a substitution, right? So this is my let's go ahead and identify everything, and then that'll help us to figure out what the product should be and all that. So this is my nucleophile. This is my substrate or my electrophile. And then I also need to identify, let me change this other piece over here because I don't want to confuse you. Let me change this to something else. I'll just change it to a methyl group. All right, because then I don't want you to want to confuse you as far as the leaving groups are concerned. All right, so this is the bromine is my leaving group. All right, so let me go back up to here for 1 second. So right, it doesn't matter if it's SN1 or SN2 for a substitution, the outcome is the same. You have a substrate with a leaving group. You react it with a nucleophile, and then that nucleophile comes in. I'll go ahead and make it SN2 and displaces your leaving group. Right, so the nucleophile is now here in the place of your leaving group, and then the leaving group is here. Anybody remember what makes leaving? How do we determine if a leaving group is good or not, good or bad, from part 1?
Is it the pKa
Mm-hmm. Of the what? Of what? You're right.
conjugate acid?
Yes. You judge your leaving group ability or stability based on the pKa of its conjugate acid. Good. Right. So that stability of that leaving group is based on how stable the conjugate acid of that leaving group is. And we're going to talk more about that when we do some other examples. But let's go back to here. All right. Because this is something that we kind of hinted at when we were doing that alcohol conversion, because all of those alcohol to alkyl halide conversions were substitutions, right? So if I have my nucleophile and my substrate and I know what my leaving group is normally going to be the most electronegative atom or some other functional group that's able to be stabilized by either resonance or induction or something like that. So if we look here, let's just predict the products. What would the product be? If it's a substitution.
The nucleophile will just switch places with the leaving group.
Right. So is it SCH3? Come on, stupid iPad. Sorry. I don't want to go Kirk Franklin on the iPad. CH3 plus
The leaving group.
leaving group, Br minus. I'm gonna put some electrons around it. And that's negative. All right. So that's my product. It's a substitution. It's a SN2 type substitution because that there are a couple of things I can look at to determine that. The first is the substrate structure, right? So secondary carbons. Secondary carbons can do SN2 or SN1, but the solvent acetone being aprotic tells me that this is SN2. Right, that aprotic solvent, that's a indicator that the reaction is going to be SN2. If it's in a protic solvent, then 9 times out of 10, the mechanism is going to be SN1. It'll still be a substitution, but it'll be it'll go through a different mechanism.
Dr. Russell.
Yes.
Why did you do the dash line instead of?
No, yeah, we're going to talk about that in 1 second. I'm glad you saw that, but I did. That's why I changed the substrate to what I changed it to, so we can talk about that.
Okay.
Good question. Let's do the second one. Right? Where's my nucleophile? How do I identify the nucleophile? Like, go back to part 1. Jog your memory back to part 1. What is a nucleophile?
It has a negative charge.
It's gonna be negative.
It can be negative or neutral. And what's the main thing about it though?
The lone pair.
The lone pair. It's got to have a pair of electrons that it can donate. And that pair of electrons can come from a bond too, by the way, just like we just learned with organometallics. But it's got to be a donor of it's got to be an electron donor, right? So this is, you can see the lone pair here on this CH3 that makes that in this instance, my nucleophile. And then by default, this becomes my substrate. And if you ever have a question about what your leaving group is, find the most electronegative atom in the substrate, right? It's not going to be a carbon. It's not going to be hydrogen, right? It's always going to be some highly electronegative atom or a functional group with a highly electronegative atom, right? So if we look right here, we got an iodine. So that's my leaving group. So what's the product going to look like? And then we're going to go back and talk about the protic solvent, and we're going to talk about the change in stereochemistry.
The nucleophile and leaving group switch, and then you'll get the leaving group by itself.
So I'll have this. I'm going to change the color on that CH3. Is that right? Plus I minus, right?
Right.
All right. So that's it in a nutshell for SN2. You have to have a protic solvent. And one of the things that in the second order, so we can talk about the rate law too, but one of the things that's a hallmark of a SN2 substitution is seen right here, right? Where you went, let me change that to a different color, too much green. Right? This went from wedged to dashed, right? So that we talked about that when we did that alcohol to alkyl halide synthesis. What do we call it when the stereochemistry switches like that? Anybody remember?
Inversion?
Yep. Who was that?
Brittany.
Yeah. Be confident. You're right. It's inversion. Inversion of stereochemistry, right? It went from R to S or S to R. Let's see if we can figure that out too. Right? What's the stereochemistry of that bromine, whatever, of that stereocenter where bromine is? You know bromine is going to be 1. You know that there's a hydrogen going back already because the bromine is on the wedge. So 2 and 3 have to be on either here or here. Which one you think is 2? And how do you determine that? Come on now, we just took a test on that.
What was the question?
What's the priority of those 2 groups? We know bromine is 1.
I think the one on the left would be 2.
Yeah, I was gonna say that name.
Yeah, this is 2, and that's 3, right? Because when you get those 2 carbons are the same, so you got to keep going until you reach that point of difference. Is that right?
Yes.
So when you get to here, and you compare those 2 carbons, you see that they're different, and then one of them is branched. One of them has a substituent on it. So that's why that carbon that I have labeled as 2 is 2. So is that clockwise or counterclockwise?
Counter.
Looks counterclockwise, right? So this is S. Squeeze in here. That's S. Come on, pen. Promise I feel like I need handwriting training every time I use this iPad. And then over here, that has to be R, right? Because it's reversed. Are you following that?
Yes.
Yes.
Yeah. It's always going to switch from S to R. Let me show you why with a generic example, right? For the SN2, this is on the next page, I think. And I'm going to talk about the solvent in a second too. So this is like the basic on the left side, the basic paradigm for SN2, right? The nucleophile is, if you look here, change this pen. So the nucleophile always attacks. This is why you can't do it on a tertiary carbon. It always attacks opposite of the leaving group. Right, always opposite of your leaving group. And so because of that, that's why you always see that inversion in stereochemistry, because the nucleophile is always coming in from the opposite side of where the leaving group is. I think we talked about this a couple of weeks ago, maybe a week ago, when we were doing alcohols to alkyl halides. So that's what causes your inversion. Right? The fact that when this reaction happens, the nucleophile always attacks opposite of where the leaving group is. Never comes in from the same face. All right. So anytime you're doing an SN2, if it happens at a chiral center, that chiral center is going to get reversed. And you can see that here in the transition state. Right, you can see that here. The nucleophile is right here. It's attacking the substrate because the substrate is partially positive. Right, and then it's also the leaving group is leaving at the same time that the nucleophile is coming in. Right, so you can see that incoming nucleophile, departing leaving. What do we call a reaction where everything happens all at the same time?
Concerted.
Concerted.
Yeah, that's right. It's a concerted reaction. So I'm gonna say the rate determining step. No, let me not say that. I'm just saying the reaction occurs in one step. All right. So it's a concerted reaction. That means that there's never an intermediate, no carbocation. All this is just really just review, right? There's no carbocation intermediate, unlike the SN1 and the E1, which do go through a carbocation intermediate, right? And if we look at the we look at the energy diagram, which is shown here, you can see that, right? Your nucleophile and your, actually, I need to cut this out. So we talk about that solvation. Your nucleophile and your substrate are there, right here, right? And every nucleophile is interacting with the substrate as you go from starting material up to the transition state, right? What is a transition state? Anybody remember from part 1?
It's theoretical, I know that.
It is theoretical. That's true. That's very true. It's the highest energy point on the diagram, and it's the place where bonds are either made or well, bonds are being made and bonds are being broken at the same time, right? Anybody remember, if you look at this diagram, what type of reaction would that be? Is it exo or endothermic? And how do you know?
Is it
I
endothermic?
think it's
Yeah, it's endothermic, right? You can see because the reactants are lower in energy than the products. And you can look at the activation energy right here and see that it has a high activation energy. You following that? Exothermic will be the opposite. It will have a smaller activation energy, right? And the reason I'm showing it like this is because the attack of the substrate and simultaneous loss of leaving group is a rate determining step for SN2 mechanism, right? So it's going to have a high activation energy compared to any other steps that are in that process. Because if you can remember from when we talked about converting alcohols to alkyl halides, right? There can be like steps that precede or follow like the substitution step. Like with the alcohols to alkyl halides, we did a proton transfer and then we did a substitution and then something else may have happened, right? So it depends on which method we use, right? But this is a concerted reaction, happens on the primary, secondary carbon, and it always proceeds with inversion of stereochemistry. All right, so let me talk about the solvent real quick, and then we're gonna move on to the SM1. So if we look at, make this, stretch that out some. All right, so we look at the energy diagram. You can see the nucleophile is here, right? And it's roughly equal in energy to the substrate, right? They're roughly equal in energy. But and this is understood to be in an aprotic solvent. I'm gonna just write this up here. But if you do this in a protic solvent, it's going to have an effect on the outcome of the reaction. It's actually going to slow the reaction down. And I'll show you why. Right. So in an aprotic solvent, your nucleophile and your substrate are roughly equal in energy. But in a protic solvent, what happens is a phenomenon that we call solvation. get this. All right, so we have a process that we call solvation. And what that means is what it sounds like. So if I have a nucleophile, and let's say I'm doing this in methanol, right? So if methanol is my solvent, right? That's my solvent. Then, and I put a nucleophile in that solvent. What happens is the nucleophile gets surrounded. Let's go back and use the one we had at the beginning. Right? So all of those protons start hydrogen bonding in a sense to, because these are all partially positive here. And so this thing actually gets surrounded by protons. And this is partially positive, right? And that's bad. Anytime you surround that nucleophile, which is negative, or it could be neutral, as long as it has lone pairs, uh, or if it has a polarized bond like a granular, when you surround that nucleophile with protons, it basically makes the nucleophile lazy, right? It does the nucleophile becomes less reactive, and it lowers the energy of that nucleophile. So solvation is not good. That's why you want to do a SN2 in a protic in an aprotic solvent. Because if you're doing a protic solvent, what happens is you're gonna solvate your nucleophile and then decrease its energy.
And Dr. Russell,
Mhm.
what you drew was an example of the solvation?
Yeah. So you see how the protons on the methanol are here and here and here, right? They form like a cage around the nucleophile. So they lower the energy, make it less reactive. And then I'm gonna show you what that means on the energy diagram too. So if the energy drops, then the reactivity is gonna drop, and it's gonna slow the reaction down. Right, I'm gonna come back to that to give you a chance to write it down. But the nucleophile in a protic solvent, the energy is gonna drop to here somewhere. I'm estimating it, right? So if that's where your nucleophile is compared to your starting material, then you can see that you've also created a bigger gap in the activation energy, because it was here and now it's here. So now delta G gets increased. Let me switch pens right quick. All right, so the activation energy increases when you solvate, if that nucleophile is solvated. All right, so if you solvate that nucleophile, you're gonna drop its energy, you're gonna increase the activation energy, and you're gonna slow the reaction down, way down. All right, so that's why you run this reaction. If you're trying to do it SN2 type mechanism, it needs to be done in an aprotic solvent. Otherwise, it's going to be much slower. All right, any questions so far about anything?
Nope.
All right. So let's move to the SN1 reaction real quick. And let's go right here. All right, so for SN1, you can do this on a secondary or tertiary carbon. It's a stepwise mechanism because it goes through a carbocation intermediate, and the rate law is first order. So it's a first order reaction because it's only dependent on the substrate and the quality of your leaving group. That's what's going to control the rate, how good the leaving group is. Right. So let's look at the first example. Right. This is my nucleophile. Right. And this is my substrate over here.
Dr. Russell,
Yes.
right now we can't see you writing.
It's just a lag.
Okay.
I'm not sure why, but there we go. Technology. Come on. All right. So if that's my substrate, where's my leaving group?
Bromine.
It's bromine, right? It's not going to be one of the carbons because they're not electronegative enough. And not only that, they're terrible leaving groups because the pKa of their conjugate acid will be super high, something like maybe 40 or 50, somewhere in that area. So here's my nucleophile. This is again, a substitution. So what's going to happen?
So the nucleophile replaces the leaving group, right?
Going to replace the leaving group. That's exactly right. So it's here. That's that, right? And then plus whatever my leaving group is. In this case, it's bromine. All right. So this can be done actually done in a Protic solvent. And there's a reason for that. The reason why it's okay to do this reaction in a Protic solvent is because the nucleophile is not involved in the rate determining step, right? The rate is strictly based on the substrate. So rate, in this case, I think I already wrote it, but I'll write it again. It's K times the concentration of the substrate only, not the nucleophile. So the nucleophile is not involved in the rate determining step. So Protic solvents don't affect the rate, right? For the SN2, it does. For the SN1, it doesn't. Because it's still more than likely there's still some solvation happening, but that doesn't control the rate. What controls the rate is the loss of leaving group, which is the rate determining step for SN1. So the loss of my leaving group is the rate determining step in this reaction, and it's stepwise, right? So if you look at the start material, you can see it's a tertiary carbon. Tertiary substrates are favored, and there's a reason for that. We can talk about it. Let's talk about it on the other side, on the other page. Put a page in here. All right, so why do we favor tertiary substrates? I'm sure somebody already knows the answer to this. Somebody's thinking about it.
Is it because it's more stable?
The more stable intermediate, right? The SN1, let's just take the same one we were looking at. So here's my leaving group, right? First step is the loss of that leaving group. So you get this carbocation intermediate right here. I'm gonna put the bromine down here. Right? And then my nucleophile is gonna attack like so, boom. And then that's gonna give me my product. Right? So the mechanism is stepwise, and you always form this carbocation intermediate. So the more stable the intermediate, right? So these are the things that will increase the rate of this reaction, right? An excellent leaving group. That's going to increase the rate. Also, stable carbocation, right? That would also increase the rate. Right. So the reason why tertiaries are favored is because they give very stable carbocation intermediates.
Season's over, sir.
Right. So that carbocation stability, that's why you have that's why this mechanism favors tertiary substrates. All right. So those two things are going to control your rate: the leaving group ability and the carbocation stability. Those two things are control the rate of this reaction. It has nothing to do with the nucleophile. All right. Any questions about that, about the SN1? Also, let me give you another example, and then we're going to end with that. You can see on the second example, right? You know what the outcome of that. You should be able to predict that product, and you can see here the solvent methanol is protic. There's a list of solvents in this handout too, protic and aprotic. So I would commit those to memory. They're not. I didn't put a bunch of them on there, so. But you can see right here, the outcome, the product of this reaction should be the same. It's just on the secondary carbon. Right, let me give you, come on, Russell, get it together. All right, let me give you another example for the SN1. Right, if the SN1 happens at a chiral center, you're going to get Rasterization. So if it's happening at a chiral center, right, you get Rasterization. That means, what does that mean for to be racemic? Anybody?
That is both
Yeah.
like achiral or like chiral. They both have the same.
Well, you can have a chiral center, but what does it mean for something to be for the mixture, a mixture of products to be racemic?
Wouldn't it be
So
50-50?
Is it equal?
Yeah, equal amounts of both stereoisomers. Yeah, so let me show you an example of that. So we have something like this, right? Let's use a secondary carbon, but we're gonna make the chiral center, make the leaving group on a chiral center, right? And let's just use the same nucleophile. And we're gonna do this in, let's do it in water. That's fine. That's a protic solid. All right. When that happens, what you end up with is actually two products. You get this plus the enantiomer of it. Right, that plus the enantiomer in a 50-50 mixture. Right, it's 50-50. All right. The reason for that is simple, right? Once I go through, if I show the mechanism, right, the first step is loss of leaving group. So if I lose that leaving group, what do I get after that? Anybody?
You get an intermediate.
You get an intermediate, a carbocation intermediate, right? So that carbon has a plus charge on it, but it's really an empty p orbital, right? So my nucleophile can come in from here, or it can come in, let me move this up some, or it can come in from here. So by the nucleophile being able to attack from either side of that p orbital with no steric encumbrance, no bias in the transition state like we talked about, no pre-existing chiral center somewhere to control it, no catalyst to control it, right? The nucleophile being able to attack at either face of that p orbital means that you're going to get a mixture of enantiomers in the product. So I'm going to set it that the nucleophile can attack from either side or either face of the p orbital. I'll say either side. I don't want that to get cut off when I post this. All right, so either side of that p orbital is open for the nucleophile to attack. So that's why you get both stereoisomers, R and S, in equal amounts. All right, that's a hallmark of, just like the inversion is a hallmark of SN2, Rasterization is a hallmark of SN1, if it happens at a chiral center. All right, we're going to stop here.
What did you say?
Go ahead.
Can you repeat what you said?
For SN1, if it happens at a chiral center, it's going to racemize. For SN2, if it happens at a chiral center, it's going to invert. All right, both of those are like key characteristics of either SN2 or SN1. And sometimes that's how you can tell what happened. If you don't know for sure whether it's SN2 or SN1, and you look at the products, if they're racemic, then you can say, okay, this had to go through SN1. And if they're inverted, then you can say, okay, this had to go through SN2.
Okay, Dr. Russell.
Mhm.
Since you're done for the day, we were talking